This video is about recognizing the differences between an equation and an identity. We need to be able to prove trigonometric identities, ensuring the proof is structured in the correct form. The first thing I need to go through is definitions. So the first definition you need to know is what is an equation. So an equation contains unknown variables or quantities. E.g., you might have 3x plus 2 is equal to 11, or you might have 5x minus 2y is equal to 7. More than one variable might be involved, and this can be solved to determine the value of unknown quantities. So for the first equation there, 3x plus 2, we can rearrange and solve it. For the second equation, we need another set of equations. So we need another equation because there's two unknowns to solve it. So that's what an equation is. A formula. So what is a formula? A formula links one quantity to one or more other quantity. So links one quantity to one or more other quantities. E.g., a formula might be a is equal to pi r squared. Velocity is equal to displacement times time. So on. Okay. And this can be used to determine, for example, determine a certain quantity for a given quantity. So determine a for any given value of r in a is equal to pi r squared. So in this one, I can substitute different values of r to get a, or to determine v for any given displacement s and t. So if I know the displacement and the time, I can always work out the velocity. Okay, the next thing you need to know is the identity. What is the definition of an identity? So an identity is always true. So it's a statement that's always true for all values of the variables involved. E.g., if we have 2 times x plus y, then it's identically equal to, so we put a three line equal sign, so 3-line equal sign, 2x plus 2y. Because no matter which value of x and y you substitute in here, you're going to get the same value. Similarly, x plus y squared is identically equal to x squared plus 2xy plus y squared. Okay, so if any pair of xy are substituted, the left-hand side quantity in identity will generate same value as right-hand side in identity. So these are the equations that you need to know. So equation, formula, identity. Okay, so which of these is not an identity? So is x plus y over 2 the same thing as x over 2 plus y over 2? Yep, it's the same thing. You can separate at the numerator. So that is definitely an identity. X minus y, is it identically equal to y minus x? No, because subtraction is not commutative. So it's not the same. So we can say nope. Okay, so 3 minus 1 is not the same thing as 1 minus 3. Is x squared plus y squared identically equal to x squared plus y squared minus 2xy? So if I expand this, I normally get x squared plus 2xy plus y squared. If I subtract the 2xy, they'll go missing. So yes, it's true. So that one is true. The next one, question 4, x over y is identically equal to y over x. Nope, division is not commutative. 1 over 2 is not the same thing as 2 over 1. Question 5, x times y is equal to y times x. Yes, it's true. Multiplication is commutative. 3 times 5 is the same thing as 5 times 3. Question 6, is x minus y squared equal to y minus x squared? Yes, that's true, because if you expand this one, you get x squared minus 2xy plus y squared. And on the other side, you're going to get y squared minus 2xy. What's 2xy? Minus 2xy plus x squared. So it does work out. You get the same terms but in a different order. But obviously, when you're adding and subtracting, and change the order as well. A plus b squared is equal to a minus b squared. No, because when you expand this, you get a squared plus 2ab plus b squared. When you expand a minus b all squared, you get a squared minus 2ab plus b squared. So the middle term does not work out. Does not give the same thing. So, okay, last one, 2xy is identically equal to x plus y squared, take away x squared, take away y squared. When you expand this, x plus y squared, you get x squared plus 2xy plus y squared. So when you subtract, you get rid of it. So you're getting the same thing. So that's true. So hopefully now you have a better understanding of what an identity is. Let's go through examples now. So prove or show that cos to the power 4 theta minus sine to the power 4 theta is equal to cos squared theta, which is identically equal to 1 minus tan squared theta. So what I do is I choose the side that looks more complicated. To me, the left-hand side looks more complicated. So that's the side I'll start with. Cos to the power 4 theta minus sine to the power 4 theta all over cos squared theta. Now I know it's a difference of squares. Cos to the power 4 theta minus sine to the power 4 theta. Cos to the power 4 theta is a square number. So it's the same thing as cos squared theta plus sine squared theta times cos squared theta minus sine squared theta all over cos squared theta. Now what I do know is that cos squared theta plus sine squared theta is equal to 1 using one of my trig identities. So that becomes cos squared theta minus sine squared theta times 1 all over cos squared theta using sine squared theta plus cos squared theta is equal to 1. So when I multiply it by 1, I end up getting cos squared theta minus sine squared theta over cos squared theta. Now I can separate out the numerator, so I get cos squared theta over cos squared theta. I can actually write identically equal to everywhere here. Minus sine squared theta over cos squared theta. Now cos squared theta over cos squared theta is just 1. There's minus in the middle, so minus. Sine squared theta over cos squared theta is tan squared theta, using tan x is equal to sine x over cos x, which is absolutely equal to the right hand side. Okay, left hand side is absolutely equal to right hand side. Therefore, the statement is correct that we started off at the beginning. Okay, question 2. Show that tan 2 theta is identically equal to sine 2 theta over root of 1 minus sine squared 2 theta. In this one, the right hand side looks more complicated, so I'm going to start with the right hand side. So right hand side is equal to sine 2 theta all over root 1 minus sine squared 2 theta. Okay, I know that can be changed to sine 2 theta over root 1 minus sine squared 2 theta is the same thing as cos squared 2 theta, using sine squared 2 theta plus cos squared 2 theta is equal to 1. Okay, now when I square root the denominator, I get sine 2 theta over just cos 2 theta. Now because there's no sign in the beginning, we say it's a positive square root, yeah? So it's just cos 2 theta. There's no need to put plus or minus there. Don't make that mistake. When there is no sign in front of the square root, it's the positive square root. Okay, sine 2 theta over cos 2 theta is equal to tan 2 theta, using tan 2 theta is absolutely equal to identically equal to sine 2 theta over cos 2 theta, which is equal to the left-hand side. Since right-hand side is identically equal to left-hand side, therefore the statement is correct. Okay, show that all these cases, so A, B, C, and D. So A, we've got sine theta plus cos theta squared is identically equal to 1 plus 2 sine theta cos theta. I would start with the left-hand side. So left-hand side looks more complicated to me. So left-hand side is equal to sine theta plus cos theta all squared, which is equal to sine squared theta plus 2 sine theta plus 2 sine theta cos theta, 2 sine theta cos theta plus cos squared theta. Now sine squared plus cos squared gives me 1, so it's the same thing as 1 plus 2 sine theta cos theta, using sine squared theta plus cos squared theta is equal to 1, which is equal to the right hand side. So that is true. Okay, let's do part B. Part B, to me, the left hand side looks more complicated. I don't like tan x plus 1 over tan x, so I'll start with the left hand side. So left hand side is equal to tan x plus 1 over tan x. So tan x is just sine x over cos x. Sine x over cos x plus, again, 1 over sine x over cos x, using sine x over cos x is equal to tan x. Okay, which is the same thing as sine x over cos x. 1 over sine x plus over cos x is the same thing as cos x over sine x. So I need to cross multiply to make it over the same denominator. So I need to times this one by sine x times this one by cos x. So I end up getting sine squared x plus cos squared x all over sine x cos x. But I know this sine squared x plus cos squared x is just 1. So it's just 1 over sine x cos x, which is using sine squared x plus cos squared x is equal to 1, which is just the right hand side. So we're proving that one. Okay, let's go for C now. Let's do C here. C, which side looks more complicated? Obviously the left hand side looks more complicated. So left hand side is equal to 2 sine theta minus cos theta all squared plus sine theta plus 2 cos theta all squared. Now if I expand it, I get 4 sine squared theta minus 4 sine theta cos theta plus cos squared theta. When I expand the first bracket, when I expand the second bracket, I get sine squared theta plus 4 lots of sine theta cos theta plus 4 cos squared theta. Now what I immediately see is the minus 4 sine theta and the Sine theta cos theta and the plus 4 sine theta cos theta cancel out. Got 4 sine squared plus sine squared is 5 sine squared theta. And I've got cos squared theta plus 4 cos squared theta, which is equal to 5 cos squared theta, which is 5 lots of sine squared theta plus cos squared theta, which is 5 times 1, using sine squared theta plus cos squared theta is equal to 1, which is just 5, which is the right hand side. Okay, let's do D now. D, and to me, the left hand side looks more complicated. So I'll start with the left hand side. So I've got sine squared x cos squared y minus cos squared x sine squared y. Now what I can see is the sine squared, the first term, the cos squared y has disappeared. So I'm going to try to get rid of the cos squared there. And also in the second term, the cos squared x has disappeared. So I'm just going to, so the cos squared x has, so if you look at what's common between the two, what I haven't highlighted is what I want to get rid of. So I need to get rid of the cos squared y and the cos squared x. So if I, oops, I didn't write left hand side, but this. Let me just write it out. Left hand side is equal to, this is D. Okay, so I'm eliminating the cos y. So sine squared x times 1 minus sine squared y. I have to eliminate the cos squared x, so it's 1 minus sine squared x times sine squared y. So again, all I'm using is sine squared x plus cos squared x is equal to 1. Okay, which means if I expand it, I get sine squared x minus sine squared x sine squared y. Take away, if I expand the second bracket, I get minus sine squared y plus sine squared x sine squared y. Now you can see clearly these two cancel out. So all I'm left with is sine squared x take away sine squared y, which is equal to the right hand side. So I have proven the correct thing. Okay, next one. Show that for all values of theta, 1 plus sine theta plus all squared plus cos squared theta is equal to 2 times 1 plus sine theta. So again, I feel like the left hand side is more complicated here. So left hand side is equal to 1 plus sine theta all squared plus cos squared theta, which is equal to, when I expand the bracket, I get 1 plus 2 lots of sine theta plus sine squared theta plus cos squared theta. When I combine these two are equal to 1. So I get 1 plus 2 sine theta plus 1, using sine squared theta plus cos squared theta equals 1, which is equal to 2 plus 2 sine theta. When I factorize out the 2, I get 1 plus sine theta in the bracket, which is equal to the right hand side. Okay, if I look at B, so again, this one, either one will work, but I'm used to starting with the left hand side when there is no advantage from starting from the right hand side. So that's cos to the power 4 theta plus sine squared theta. And now what I realize is cos to the power 4 theta has changed to sine to the power 4 theta. So I'm assuming I have to change the cos to the power 4 theta to sines, yeah? So it's the same thing as 1 minus sine squared theta, which is cos squared theta squared. Again, the sine squared has changed, the sine squared here has changed to cos squared. So I'm going to replace the sine squared here with 1 minus cos squared theta. Let's see where that gets me. So this is using the same identity, which is sine squared theta plus cos squared theta is equal to 1. Okay, if I expand that bracket, I get 1 minus 2 lots of sine squared theta plus sine to the power of 4 theta plus 1 minus cos squared theta. If I look at it, I still have this sine squared theta that I don't want on the right hand side. So let's try to eliminate that now. So I get 1 minus 2 lots of 1 minus cos squared theta plus sine to the power of 4 theta plus 1 minus cos squared theta. Again, using the same identity, so I'm going to write it down. Okay, now if I expand the bracket, I get 1 minus 2 plus 2 cos squared theta plus sine to the power of 4 theta plus 1 minus cos squared theta. So if I look at that, the 1 plus 1 take away 2 cancel out to 0. Okay, we get sine to the power of 4 theta, which is good. And plus 2 cos squared theta minus cos squared theta is plus 1 cos squared theta, which is just 1 cos squared theta, which is right hand side. So that's worked out. So it's always about keeping an eye on what you're aiming for and try to aim for that. Eliminate what you don't need, really. Okay, simplify these ones. So A, B, C, D, and E. So 1 minus cos squared half theta. Because 1 minus cos squared theta is equal to sine squared theta, it's the same thing as sine squared half theta. So again, I'm using sine squared x plus cos squared x is equal to 1. But our x here is half theta. B is sine theta over tan theta is the same thing as sine theta over cos theta. Again, I'm using the identity sine x over cos x is equal to tan x, which is the same thing as sine theta times, flip the second fraction over, cos theta over sine theta, which means the sine thetas cancel out. All I'm left with is cos theta. See? Okay, 1 plus sine x all squared plus 1 minus sine x all squared plus 2 cos squared x. Okay, I'm going to first expand both the brackets, so I get equal to 1 plus 2 lots of sine x plus sine squared x plus 1 minus 2 sine x plus sine squared x plus 2 lots of cos squared x. So what I realize is I've got 2 sine x here and 2 minus 2 sine x, so they cancel out. 1 plus 1 gives me 2. And then I've got sine squared x plus sine squared x, which is 2 sine squared x plus 2 cos squared x. Now what I realize is I can factorize the sine squared, 2 lots of sine squared plus 2 lots of cos squared into 2 times sine squared plus cos squared. And I know this is equal to 1. So then I get 2 plus 2 times 1 using sine squared x plus cos squared x is equal to 1, which is just 2 plus 2, which is just equal to 4. So that's the answer for this one, B. This is the answer for C. Let's do D now. I've got sine to the power of 4 theta plus sine squared theta times cos squared theta. If I factorize out the sine squared theta, I get sine squared theta times sine squared theta plus cos squared theta, which I know is just 1. The bracket, everything inside the bracket is equal to 1. So which is equal to sine squared theta times 1 using sine squared theta plus cos squared theta is equal to 1, which is just sine squared theta. Okay, E, sine to the power of 4 theta plus 2 sine squared theta cos squared theta plus cos to the power of 4 theta. By looking at this, I know that I can factorize this. So if I factorize it, let me just go to the next line. The same thing as sine squared theta times sine squared theta will give me the sine to the power of 4 theta. It must be times but plus cos squared theta plus cos squared theta there as well. So when you expand it, you get what you initially started off with. Now we know both of these are equal to 1, which is equal to 1 times 1, using sine squared theta plus cos squared theta is equal to 1, which is just 1. Okay, the last question I'm going to go through. So prove that sine A over 1 plus cos A plus 1 over cos A plus sine A is equal to 2 of sine A. So for this one, I'm going to start with the left-hand side. So sine A over 1 plus cos A plus 1 plus cos A over sine A. So I'm going to cross multiply. So that means I need to times this one by sine A and times this one by sine A. But I need to times this one by 1 plus cos A and times this one by 1 plus cos A. So what I end up getting is sine squared A plus 1 plus cos A all squared all over 1 plus cos A times sine A. So if I expand the bracket on the top, let's not expand the denominator unless we need to. So if when I expand the top, I get 1 plus 2 cos A plus cos squared A all over 1 plus cos A times sine A. Now what I do know is sine squared A plus cos squared A will give me 1. So I end up getting 1 plus 1 plus 2 cos A over 1 plus cos A times sine A, using cos squared A plus sine squared A is equal to 1. Okay, so which is the same thing as 2 plus 2 cos A all over 1 plus cos A times sine A. But that can be factorized in the top numerator can be factorized into 2 times in bracket 1 plus cos A all over 1 plus cos A times sine A. So the 1 plus cos A and the 1 plus cos A in the numerator and the denominator cancel out. So I end up with 2 over sine A, which is equal to the right-hand side. So that's part 1 done. Find the values of x between 0 to 360 if sine x over 1 plus cos x plus 1 plus cos x over sine x is equal to 1 plus 3 sine x. So sine x over 1 plus cos x plus 1 plus cos x over sine x is equal to 1 plus 3 sine x. Now, using the previous answer, we know that when x is a is 2 over sine a. So we can change the left-hand side of this equation to 2 over sine x, because we've just proven that it's equivalent. Okay, which is a much simpler equation to solve. Okay, so now what I need to do is multiply through by sine x, both sides. So I get 2 is equal to sine x times 1 plus 3 sine x, which means 2 is equal to sine x plus 3 sine squared x. So if I take the 2 over to the other side, I get a quadratic, which is 3 sine squared x plus sine x minus 2 equals 0. If I factorize this, I get 3 sine x times sine x. I get a plus 1 here and a minus 2 here, which means either 3 sine x minus 2 equals 0 or sine x plus 1 equals 0. The second equation is easier to solve, so let's solve that. X is equal to inverse sine of negative 1. I know between 0 and 360, there's only one solution at 270 degrees. The first equation, that means sine x is equal to 2 over 3. So x is equal to inverse sine of 2 over 3. If I put that into my calculator, I get 41.8 degrees. If I think of the sine graph, 41.8 is somewhere here, which is here. I've got that one. If I want to find this one, I have to do 180 take away 41.8, because this is 180. 180 take away 41.8 is 138.2 degrees. There's two solutions for that one. So those are all the solutions.